Hello everyone. We are going to introduce our work, which named Exploring GNN-based Program Embedding Technicals for Binary-Related Tasks. My name is Guo Yixin. I will present our work from the following four aspects: background, methodology, evaluation, and conclusion. In recent years, neural network technicals have been applied to an increasingly wide range of program analysis tasks. The key to analyzing programs with the help of deep learning technicals is to build proper program embeddings. However, most existing approaches use the source code, AST, and IR as a basis for building embeddings. Over the course of from IR to final executables, a number of compilation optimizations are performed, and thus the code is changed to varying degrees depending on the compilation configuration. This makes these methods unable to handle analysis tasks that are closely related to compilation optimization or hardware architecture. The existing binary-based embedding methods do not take full advantage of all unstructured semantic information and structured graphing programs. To this end, we propose a new binary-based model that makes full use of the semantics of the program's instructions, as well as the existence of multiple graph structures in programs. There are numerous graph structures in a program, including the control flow graph, code graph, data flow graph, and more, which represent a variety of program semantics, such as the control execution, data value semantics, intra and inter-procedural structure semantics. We construct program embeddings through procedure level and program level graph structure analysis. We construct control flow graphs for all procedures and use the semantic of instructions as the initial embedding of nodes. We consider the instruction token sequence of a basic block as a sentence and use BERT model to embed them. In order for BERT model to know the relations between different tokens and different sentences, we designed three tasks to train the model. Once the initial embedding of each node is obtained, the graph neural network can be used to know the structural semantics and generate graph embeddings. After completing the embedding of each procedure, we start the program level analysis. We first generate a cloud graph for each program. Each node in the graph represents a procedure, and its initial embedding is a control flow graph embedding generated in the previous step. In addition, a data flow graph is also generated for each program. The semantic information of the instructions is also used as the initial embedding of the nodes. Finally, the code graph and data flow graph embeddings will be obtained separately with the help of graph neural networks. In summary, we generate procedure level and program level embeddings through the following steps. First, disassemble the binary of a program and generate three types of graphs. Second, generate initial embedding for control flow graph and data flow graph nodes using the trained BERT model. Third, generate graph embeddings for all control flow graphs. Then use graph neural networks to obtain procedure level and program level embeddings for code graph and data flow graph. Finally, concat the results of step 4 and 5 to get the complete procedure level and program level embedding. To verify the efficacy of the model, we conduct two experiments that are highly related to compilation configurations: binary similarity detection and date store prediction. We use a POJ dataset and spec dataset to complete the tests. To test the impact of different compilation configurations, we compile all programs with two compilers and two compilation options. For binary similarity detection task, each sample consists of two binary. The model will construct embeddings for each of these two binary and output their Euclidean distance, which we take as a similarity distance. These two figures show the distribution of similarity distances. The x-axis indicates the similarity distance, and y-axis the number of samples. For binary pairs from the same source code, that is, the blue bars, smaller similarity distances are better. It can be seen that our model has better differentiation capabilities. We also tested the ability of the model to distinguish between different compilation configurations. whether classifying the 4 compilation configurations or the 2 compilers, we achieve better results than other methods model. In addition, the results of the model breakdown tests demonstrate the necessity of fusing multiple types of graphs. Next, for dead store prediction task, all procedures will be divided into 2 categories: those that contain dead store problems and those that do not. We use 3 metrics to measure the effectiveness of the model, namely accuracy, precision, and recall. From the figure, we can see that all measurements are beyond 75%. This shows that our method can effectively accomplish the dead store prediction task. Now I'm going to summarize our work. We built program embedding based on the binary, offering the possibility to analyze compile-related program analysis tasks. We abstract a program into multiple graphs, extract different program structure information, and perform multi-dimensional analysis of the program. We perform procedure level and program level analysis, capturing both local and global features. We measure our model on 2 tasks and achieve good results. These are all our work. Thank you.